Stay tuned on Chemistry of Hybridization of Orbitals, and kindly be patient with the passionate and energetic Mr. James, the Decomposer, as he'll be enlightening you, so just continue to watch this lovely video. We hope and wish you'll enjoy till the end. Stay blessed.
And today we'll be focusing on what we call hybridization. So in a way, people are still struggling to can identify to find the hybridization state of a carbon, for instance. You know what I'm saying? So today I'm going to be covering on those things, you know, maybe a few things like sigma bonds, pi bonds. You know what I'm saying? This is part of inorganic chemistry in a way, and a little bit of organic. But yeah. Okay, so guys, you gotta check this out. All right, now let's talk about hybridization. Hybridization. When you talk about hybridization, Bafetu, my guys, my people, my family, we're talking about what? A process of mixing of orbitals. So whenever the orbital starts to mix, you know, they start to mix, like maybe an s orbital, one s orbital mixes with 2p orbital, for instance, that's the result, the process in which when the one s orbital, for example, if you have something like this is basically called CH4, which we all know the molecular name is called methane. So if you have to draw the Lewis structure of this molecule, it's gonna look like this, okay? We basically have that, okay? So now you need to know that the hydrogen. Maybe some people do not know what is an orbital. Okay. Let's take it easy. What is an orbital before I come here? Okay. So we said hybridization is a what? A process of mixing what? Mixing of orbitals. Okay. And then now there is something called orbital. Orbital. What is an orbital? So I usually like to say that an orbital is basically a region or a place in which an electron may be found in an atom. That's what I say. Okay, so I say that an orbital is a region or a place in which an electron may be found in an atom. Okay, in an atom. So guys, this is one thing you must know. We all know that the atomic structure looks like this, right? This could be an atomic structure. This could be the atomic structure of what? Maybe we can make use of, let me see, 2 and then 8, which is 0, 10. Let's say sulfur, for instance, or sulfur or chlorine, right? Let's make use of this guy, chlorine. So I'm gonna try to draw, right? So I'm gonna put 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so 1, 2, 3, 4, 5, 6, 7, 8. Okay, remember that the first energy level must only occupy two number of electrons. Okay, so that's why at the ground state you only have 2 electrons. Okay, that is the ground state. That is the first energy level. Okay, and then which is your lowest. And then there comes the second energy level. The second energy level, for it to can be stable, for it to can be full, it only requires or need about 8 number of electrons. Then it's full, it's stable, okay? Then if there are still more electrons that are needed in this structure of an atom, then we should add another energy level. That's why we had to add another energy level. So we're gonna have, so basically if you check, 2 plus 10 is already like 2 plus 8 is probably 10, right? Not probably, but it is 10. So you only have like 10, which is like your magnesium in this case. Could be like your magnesium. No, what's this? Neon is basically like neon, right? And then let's just make it magnesium, which is like Mg, okay? So I could put 1 and 2, okay? Now remember that magnesium is found in group 2 in the periodic table. So it means that everyone who is in group 2, they will have a valence electron of 2. Anyone in group 2, calcium, barium, strontium, all of those elements in group 2, they will have valence electron. They will have 2 number of electrons, which are the valence electrons, by the way, okay? So now here's the most important part. We all know that in a structure of an atom, inside of the nucleus, we have what we call protons and neutrons, okay? Protons are positively charged. Neutrons, they are basically neutral. They are not charged in a way, right? Because we have 2 types of charges, negative and positive. Positive is a proton, and negatively charged particles that are always found in an atom surrounding the nucleus, we call them the electrons, okay? So they are always orbiting around the nucleus. They're like planets. Electrons are like planets, always evolving around the sun, in a way. So now here's the most important part, guys, that you need to put in mind. This is what happens. You need to find an electron, right? When you look at the structure of an atom, it seems like electrons, this is where they stay, but that's not the case. Electrons, they have their own shelters. So as they are busy orbiting, as they're busy moving around, as they're busy like moving around the nucleus, moving around these energy levels, they are in a shelter, they are in a house, they are in a room. That room, we call it what? An orbital. So an orbital, we say, is a region or a place in which an electron may be found in an atom. Okay? So there is a formula, but I'll introduce it on the next video. There's a formula which we use to determine the speed of an electron as it's moving, because it's impossible to that's the principality of or the principal uncertainty principle, which tells us that it is not possible to determine the speed or the velocity and the displacement, or the distance, basically we can say the displacement of an electron in an atom. Okay, so we can actually start by finding one, then we can get the other one. Okay, because the electron has the momentum at the end of the day, because of it has a mass and there's a speed, so it definitely has a momentum and all that. But it's not possible to find the position, which is the displacement, the position at which the electron is at. Because electrons are always, so how will you be able to you know what I'm saying? So yeah, the most important thing, which was the goal right now, was to show you guys that no, an orbital is basically a house, a room. Okay, for example, if you are now at work, okay, if now you are at work or now you are at school, basically you are in a class. So if they were to say maybe there is someone is looking for you, okay, they say they're looking for Mr. James. Okay, someone's gonna go to the office or the receptionist, and then they will tell you Mr. James is, you get what I'm saying? So you'll find Mr. James there. He's in that room. You are in that classroom. So students are always in the classroom. So the classroom is basically an orbital. Okay, electrons are those students in the classroom. You get what I'm saying? So that is actually what an orbital is. We have different types of orbitals, which is very much important. Okay, now let me just mention them. Okay, now types of orbitals, the types. Number 1, we have what we call the s orbital. The s orbital is called, it's the shape of it, the shape of the s orbital it's spherical. It's spherical. And then number 2, we also have what we call p orbital. So, which is a dumbbell shape, it's a dumbbell shape, but people call it principal, this one, right? It's a principal. It's a principal. Then we have number 3, I can just mention, there are 7, okay, I'll try to mention them. And then there is a 4th one. This one, let's call it what? S, P, D, and then F, G, H. I don't know if I missed. They're about 7, if I'm not, they're about 7. Eh? But yeah, spherical principle, and then I'll just make use of this only 5. Only this 4. So this one, it's a D, we call it diffuse, and then this one is just called fundamental. Okay, fundamental. Okay, fundamental. So it's very much important, right? You know all this for inorganic chemistry, definitely, whether you're in university, college, still in high school, you need to know that these, on the periodic table, basically, these are the things that you need to know, especially when you're dealing with electron configurations and all that, important stuff. So, one, the s orbital can only occupy the maximum number of 2 electrons. Please put in mind. Okay, each and every orbital, listen to me carefully. An orbital can only occupy the maximum number of 2 electrons. There must never be 3, but 2. Okay, with parallel spins like this. Okay, so whenever, the shelters are full and all that, you will see electrons having to they will have to squeeze each other in the rooms. Electrons, they are both negatively charged. Okay, both negatively charged. Now what happens is that there's going to be a force of repulsion. This is why we're going to end up having some exceptions on ionization energy and electron affinity in a way, So that's why we have exceptions there. Ionization energy and electron affinity because of the electron repulsion. When you're looking at the trends of the periodic table and the atomic radius, these are the things that contributes there. Okay, so please keep that in mind. An orbital is something that looks like this. Inside an orbital, there could only be 2 number of electrons inside, not more than that, only 2. Okay, and if it's full, the electrons must slip or must be in opposite direction, parallel spin like this. Okay, that is Pauli's exclusive principle, Hans rule, Aufbau principle. They are the ones that needs to be followed when you're dealing with electron configuration. Okay, now here's the most important part that I want to mention. The s orbital will always be like this, Buffet 2. Okay, this is basically the s orbital. Okay, then we have the p. The p orbital has how many orbitals? It has 3. So this is the p orbital. It's something like looks like this. Okay, so the p orbital will always have 3 orbitals. It has 3 orbitals. When it has 3 orbitals, how many number of electrons must we expect? Now, remember we said each orbital must get how many? 2 electrons. So just say 2 times 3 because there are 3 orbitals and each orbital must have how many? 2. So 2 times 3 is what? 6. So I'm expecting 6 electrons. That's why we're going to have 1, 2, 3, 4, 5, 6. So there we go. You get what I'm saying? This is how you identify. You get what I'm saying? No more matata, no more genga, no more problem. Then here's another thing that we must identify as well. When you come to diffuse, okay, the D part. When you come to the D part, that one, okay, there we go. We're gonna have 1, 2, 3, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So there are 5. There are 5 in this case. Here you have 5, right? So if you have 5 and there are, so basically you're gonna have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, they are 10. We must expect how many electrons? 10 electrons because of they are 1, 2, 3, 4, 5. 5 orbitals times 2. Why do we multiply by 2? Because each and every orbital will only be occupied by how many number of electrons? 2. So that's why we say 2 times 5, which gives us 10. Then we're going to have 10 number of electrons. That's what diffuse, your d orbital. Okay. Then the last one which I'm going to mention is that fundamental, which is our f orbital. Now our F orbital is gonna have 7 orbitals. Okay, I can put it here, 7 orbitals. So it's gonna be 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Maybe something like this. 1, 2, 3, 4, 5, 6, 7. There are 7. If there are 7 orbitals, and we all know that in each and every orbital there must be 2 number of electrons. It means we must expect how many number of electrons in total in this F orbital? 14, because we have 7 and then 7 times 2 is 14. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, sorry. 1, 2, 3, 4, 5, 6, 7, 8, 9. This one is not. Okay, so let's start again. Should make sure that everything's correct. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So they are now 14. So guys, these are the orbitals that you guys should know for now. The S orbital, P orbital, the D orbital, and the F orbital. Okay, then there is GH, which they all differ in terms of the number of orbitals and the number of electrons that are going to be occupied in there. Ne? Okay, good stuff. So if you now understand what an orbital is, I guess you can now move with me along the hybridization. Okay, let's move on. Let's move on. So your task in the meantime, guys, is to try to know about the G and H. What about the G and H? How many electrons should we expect and how many orbitals are there? Okay, that's your homework you can try to do in the meantime, all right? And then now, we also have something called the hybrid, okay? The orbital hybrid, or should I say hybrid orbital? Okay, let's call it hybrid orbital. And unhybridized orbital. Okay, so hybrid orbitals, they form sigma bonds. And then we say that unhybridized orbital, they form what we call pi bonds. These ones, they form pi bonds. Okay? Pi bonds looks like this, and then the sigma bonds, there might be something that looks like that. Okay? It's like a theta if you're doing mathematics, like a theta. Someone may write it like this, which would look like a flux when you're doing a physics, you know what I'm saying? But yeah. So hybrid orbitals, they always form sigma bonds, and then unhybridized orbitals really form pi bonds. Okay, I'm going to show you the difference or how to identify the hybrid orbital to identify sigma bonds and pi bonds on different types of molecules. All right, good stuff. Okay, so now let's talk. Remember, we are together on this one. We are together. All right. So there are a number of things that I want to make sure I don't miss out. Here it is. So if you have a single bond, we are talking about one sigma bond. We have one sigma bond. Okay. If we have double bond, we have one sigma bond and one pi bond. One sigma bond, one pi bond. So pi bond starts to be available or to exist or to occur whenever we have double bonds and triple bonds. But with single bonds, we don't have pi bonds. So we only have what? Sigma bonds. So sigma bonds are always there. Okay. So in this one, you also have what? One sigma bond and two pi bonds. Okay, so always know triple bond forms two pi bonds, double bond, one pi bond. In each and every bond, there is a sigma bond. Okay, always know that pi bonds, they start from double bond. Whenever we have triple bond, that's when we have two pi bonds. Okay, that is one thing I wanted to mention with you guys. Very much important. when I'm going to be doing some structures, you're going to be able to have a full understanding in terms of how to identify these two. Okay, good stuff. Or maybe is there anything I must put on? Okay, now this is very much important. Today I'm using a script because usually a lot of people don't know that today I'm using a script because this is chemistry and I gotta make sure I don't leave anything behind, right? Okay, so I mentioned that hybridization is a process of mixing of orbitals. Now, this is what happens when we are looking at that CH4, né? Because I was basically here before I had to tell you what an orbital is, right? So guys, I want you to know something that the 1s orbital is basically found in the lowest energy level, right? The 1s orbital. So hydrogen, since it has 1 electron, 1 proton, and is the first element in the periodic table, so it has an s orbital only. So we are expecting this guy, okay, to can bond with something like this. Isn't that awesome? So now it's an s orbital. I'm gonna show you. It's an s orbital with sp orbital. So this is what we're having. Okay, an s orbital with an sp orbital. But I'm not gonna really call it sp orbital because this guy is basically sp3. This guy is called sp3. But I'm gonna tell you why do I call him sp3. This carbon is called sp3. I'm going to tell you why do we call it sp3. There are different types of hybridization which I'm going to show you before. Let me just mention them quickly. Types of hybrids. Number 1, we have sp, sp2, sp3. There is also sp3d to the power 1 and so forth, but for now I just want to work with this ones, okay? All right, now this is very much important, guys. When you this one, I'm gonna show you something. This guy, the sp3, we have a tetrahedral shape, okay? When you have a tetrahedral shape, a molecular geometry which is tetrahedral shape, which has 4 bonds like this guy. Look, this carbon has 1, 2, 3, 4. This meaning we have 4 bonds. When you have 4 bonds, we're gonna have an sp3 hybrid or hybridization, okay? And then when you have sp2, this is when we have a trigonal planar. Trigonal planar, by the way. So this is when you have this guy. You remember NH3, or I can say like something like this, OBH3. OBH3 is a trigonal planar because of the shape. It's going to look like this. Okay, the shape is going to look like that. So that's a trigonal planar because it has no lone pairs. But if it's a trigonal bipyramidal, or trigonal pyramidal in a way, it's so NH3. NH3 is different from this guy because it has lone pairs, this guy, okay? Yes, I understand. I understand that the central atom is attached to 3 atoms. Even this one is attached to 3 atoms. But because of this guy has no lone pairs, he has nothing on top. It makes him a trigonal planar. But because of this guy has the 2 lone pairs on top, it makes him who? A trigonal pyramidal, by the way. Okay, so they differ in terms of the angles that they form as well. Okay, this one is like 104.5 degrees and so forth. Yeah, okay. So this one, which is your SP, is our linear. This forms a linear shape. This one usually see it whenever you have like CO2, like carbon dioxide, right? Because this is what it looks like. We have 2 oxygen atoms, so we must have 2 oxygen atoms, and oxygen likes to form 2 bonds. It likes to form 2 bonds, okay? So that's why it formed 2 bonds, no lone pairs. So that's linear. The reason why we say this linear is the shape is linear, the molecular geometry is linear. It is because of this carbon. It is less electronegative, and these two are more electronegative. So the oxygen, this side is going to pull the electrons towards itself. Even this one pull the electrons towards itself. So in a way, the dipole moment is 1, 1. So since they are going opposite direction, it makes the dipole moment here 0. And whenever the dipole moment is 0, it means it makes this molecule to be non-polar. When it's non-polar, it is symmetrical. Okay, a symmetrical shape tends to be non-polar, and unsymmetrical shape tends to be what? Polar, because of there's gonna be unequal sharing of electrons. Okay, awesome. I'm gonna make more videos. Check also the other video of aqueous that I made of chemistry. I mentioned the difference between polar and non-polar. So check it out. Right? No dipole moment, no polarity. In other words, okay? Because dipole moment is the measure of the polarity of the within a molecule. Okay. So let's continue now. Let's continue. So the types of hybrids that you guys are always gonna come across. These are the main ones. Okay. These are the main ones. Right. So here I want to show you guys something. I told you that whenever we see sp3, we must see a tetrahedral shape. So there must be 4 bonds. You can see that the central atom made 4 bonds. Look, 1, 2, 3. Look, 1. Maybe someone wants to count with me. 1, 2, 3, and 4. There are 4 bonds. So this carbon will have the sp3, will be sp3 hybridized. So that's the hybridization of this molecule methane. Okay. Now, what about the hybrid of hydrogen? Since it's 1 bond, it forms 1 sigma bond, which is 1 sigma bond. It's gonna be S. So S, 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 S. Okay. So that is how you form, or we show or we identify these guys. Né? Let me show you something else again. That is more interesting. Don't worry. Okay, I hope you still have the picture. All right. And then there is something that I'm not forgetting, is it? Awesome. Now, this is what I wanted to show you guys. So if 4 bonds, we talk about sp3. To put a summary, number 2, 3 bonds. 3 bonds, we'll be talking about sp2. And then 2 bonds. 2 bonds, we talk about sp. And then number 4, which is 1 bond, that's your S. Okay? That's your S orbital. So these are the 3 types of hybrid. These are the 4 types of hybridization. So when you see 4 sigma bonds. No, I'm sorry, my people. I'm really, really sorry. This is supposed to be sigma, ne? Supposed to be sigma. 4 sigma, sigma, sigma. Okay. If you see 1 sigma bond, you're gonna have S hybridized. And then if it's sp hybridized or hybridization, then you must know that in a molecule you have 2 sigma bonds, okay? If you have 3 sigma bonds, you're going to be having sp2 hybridization. If you see 4 sigma bonds, you're going to be having sp3 hybridization, okay? Now, let me try to show you something before I give you guys some exercises, okay? Work with me, guys. Work with me! Okay. Okay. Let's just say we have this molecule, CH3. We have C, there we go, another CH3, eh? Oh, then CH. Now, let's identify the hybridization state of carbon, okay? And maybe hydrogen as well, okay, of each. Now, let's check here. How many sigma bonds do we see here? Look, sigma bonds, we said Remember, one sigma bond. Basically, sigma bonds are formed by overlapping of atomic orbitals. Ne? So the overlapping of atomic orbitals, they form sigma bonds. And I want to mention something, guys. When you see something like this, I didn't draw it nicely, okay? But this guy means the tail, this guy means the head, okay? The reason why this guy is the head is because of he has most of the density of the electron bond formation. Ne? He has the most density of the electron bond formation, this guy, the head. So that's the larger loop, and then this one is the smaller one, okay? The small loop. So this is basically the overlapping, the mixing of orbitals. So the mixing of orbitals forms what you call a hybrid. So a hybrid orbital is the result of the mixing of those orbitals. So maybe one s orbital with the 2p orbital, you know what I'm saying? Yeah. But what happens is that whenever these guys overlaps in a way, for example, the sp3 of CH4, this guy is basically formed because of the 2s and the 2p, because of they have like the amount of the energy, it's really quite equivalent in a way at some point, you get what I'm saying? So one s orbital is gonna mix or overlap with the 2p orbital, okay? And then that's when you're gonna end up having the sp3. Okay guys, I'm gonna show you more of this thing so that you can have a better understanding. Those that are lost here, okay? But those are not lost. Okay, let's move on, guys. So here's an important thing, guys, you should know. This guy has an s orbital, right? Let's talk to him. Let's talk to him. So my guy, you are the s orbital. You're the s hybrid. He's the s. He's the s hybrid because of there's a one bond, okay, one sigma bond. But what about this carbon? How many pi bonds? How many sigma bonds does it have? Because we said a hybrid orbital, we see it by forming sigma bonds, and hybridized orbital forms pi bonds, okay? So now you can see here we have, how many pi bonds do we have? 2 pi bonds. We have 2 pi bonds because we said a double bond has a 1 pi bond, triple bond has 2 pi bonds. So you can see there's already an hybridization there. You get what I'm saying? So we have 1 sigma bond here, it's 1 sigma, and what about here? Is another one. So basically what happens here, if there are 2 sigma bonds, this carbon has 2 sigma bonds. So who is that? Sp. So this guy here is Sp. So this carbon is Sp what? Hybridized. I don't know if this color blue is visible there, guys, alright? Don't know. So we say hybridized. So Sp is, this carbon is Sp hybridized. This guy is just S hybridized. What about this carbon here? This carbon here also has 1 sigma bond and 1 sigma bond. So since there are 2 sigma bonds, and we said 2 sigma bonds forms Sp hybridized, so it means this carbon will also have what? Sp hybridized. Sp hybridized. Okay, so this is how you show the state of the hybridization of carbon atoms or different types of atoms in a molecule. Then you look at this guy. This guy is CH3. When you pluralize him, when you simplify him, when you unfold him, you're gonna start seeing something that looks like this. This guy is the same as 1, 2, 3, then that is this bond here. So you can see 1, 2, 3, 4. Huh? So there are already 3 plus 4. And we said whenever we have 4 sigma bonds, we talk about 2 sp3 hybridized. So this guy is going to be called sp3 hybridized. Hybridized. So that is how you identify the state of hybridization of different types of molecules. Okay. Now, let me give you guys some questions. I hope this one was easy. Or should I do another one? Let me try to do the last one as an example. Okay. Okay, now, how about we do this one? How about we do CH3, this guy with a double bond, and we also have a CH3 here. Okay, now this one, let's show the hybridization state of each and every carbon in this molecule. Okay, now if you look at this carbon, it's CH3, so there are already 3 bonds, 3 sigma bonds plus another one here. Remember I told you that CH3 is the same as 1, 2, 3, then there's another one here which is the 4th one. 4 sigma bonds makes who? sp3. So this guy is sp3 hybridized. Okay, and what about this carbon? Now you need to pay attention. There is a double bond. Okay, the double bond makes 1 sigma bond and 1 pi bond. Whenever we see single bonds, there are no pi bonds. The more you see double bonds, triple bonds, that's where pi bonds comes in. Okay, so here we have 1 sigma bond, 1, 2, 3. There are 3 bonds. 3 sigma bonds makes this guy to be the sp2. So this guy is going to be sp2. Why do we say it's sp2? It's because of there are 3 sigma bonds. 1, 2, 3. And then what about this guy? This guy, he is the same as this guy. So it's going to be sp3 hybridized. So this is how you show the hybridization state of each and every carbon or atom within a molecule. Okay, awesome. The last thing that you guys must put in mind, sp2 double bond, triple bond sp. Okay, sigma single bonds sp3, the summary. So basically this guy, when you see sp3, there must be single bonds. And then whenever there is double bond sp2, single bonds, triple bond sp. That's just the summary. Ne? Okay, those who got me. Those who didn't, you have to restart the video again. You know what I'm saying? Okay. Now, I would encourage you guys that right now, when I'm about to show you the exercises, you can pause the video and try to attempt the questions by yourselves, né? And then check yourselves afterwards. You know what I'm saying? But I believe in you guys. You know what I'm saying? You got this. All right. Now, let's do it. Let's do it. So here's the first question. The first question is number 1. We have CH3SH. Now we need to show the hybridization of this molecule, the entire molecule basically, right? Because of obviously there is 1 carbon, so our main goal is to check the carbon there. Okay, so let's write it nicely. You can actually draw the Lewis structure if you can't really, simplify this matter. So you can say 1, 2, 3, and then you have the S, you have the H. Okay, people might be wondering, why do I really have to show these 4 dots? Those 4 dots are the lone pairs, all right? Because sulfur comes from group number 6, which is with oxygen, and group number 6 is called the octogens, and the octogens likes to bond with 2 bonds. They like to form only 2 bonds, all right, so that they can be stable to satisfy the octet rule. So you can see that this guy already formed 2 bonds, and then he's left with those. So 1, 2, 1 in each and every single bond. There are how many electrons? 2. So 1, 2, 3, 4, 5, 6, 7, 8. So this guy is stable. Hydrogen is 1 electron. For it to be stable, it needs 2 electrons. So 1 from each and 1 from the sulfur makes it 2. It's also stable. Isn't this nice? Okay, but that's not the goal. The goal is to identify whether this guy he falls under which type of hybridization. Now let's see. We can see that this guy is 1, 2. Look. 1, 2, already this guy is sp3, so this guy is going to be sp3 hybridized. Okay, so he is sp3 hybridized, sp3 hybridization, as you can see. And then number 2, our number 2 question is going to be, maybe I should erase this one and do it here. Our number 2 is going to be C Okay, we have H, H, and then you also have the double bond of nitrogen and H with lone pairs there. Okay, yeah. So now we need to identify something. You can also see, okay, someone might also be asking about it. Now, guys, nitrogen comes from the nitrogens, which is group number 5, close to oxygen and between oxygen and carbon, right? So group number 5 atoms or elements, they like to form triple bonds. So you can see 1, 2, 3 bonds, okay, for it to be stable and to satisfy the octet rule, because they are having 5 valence electrons, and for them to be 8, there must be 3. So already 1, 2, 3, 4, 5, 6, 7, 8. This guy is stable. We're good. We're good. Now check this guy now, this carbon. What kind of hybridization stage do we have in this molecule? Now, how many sigma bonds does this carbon has? 1, you see 1, 2, there are already 2 sigma bonds. Because of there is a pi bond, a double bond makes 1 pi bond. And in 1 pi bond, or that double bond, there is always a 1 sigma bond. So, which is 1 sigma, 1, 2, 3. Since there are 3, we said it's going to be what? sp2. So this guy here is going to be called sp2 hybridized or hybrid. sp2 hybrid. The whole molecule is sp2 hybridized because of this guy. Remember checking the carbon state. Okay, then let's go to the third one, which is C or number 3. It's going to be, we're having S and the double bond here, carbon. And then there we go. So I need to determine these guys here. 1, 2, 3, 4. 1, 2, 3, 4. These lone pairs are very much important, okay? You can see this guy is linear, by the way. And oxygen is electronegative, is going to pull on that side. This guy pull on the other side. So it makes this guy to be linear because it's going to be symmetrical, because there is equal sharing of electrons in a way. You get it? There is the dipole moment is 0. The dipole moment is 0. You can see it's 0 because that guy pulls to the east, which is right. To the left, then they cancel out at the end of the day. So it's symmetrical, it's linear shape, which is 180 degrees. Now, what about the state of this guy? How many sigma bond? 1 sigma bond, 1 sigma bond. Because I told you that in a double bond, there is always 1 sigma bond. Okay? And we have how many pi bonds here? 2. 1 pi bond, 1 pi bond, because a pi bond starts to exist whenever you see double bonds. Okay, so 1 sigma makes how many bonds? Since we have 2 sigma bonds, it means we're going to have what? This guy is going to be called sp hybridized. sp hybridized. This guy is sp hybridized because of there are 2 sigma bonds. 1, 2. Remember what I've said, guys. Alright? Alright. Then let's go to the last one. The last one is gonna be C, which is the 4th one. It's gonna be C, and then a triple bond, and then I see H here and H here, right? Okay. Then now let's check something. These carbons here, we have 2 carbon atoms, so which is a bit crazy, right? But yeah, it's cool. Now this carbon, it has 1 sigma bond. Remember the triple bond. If you see a triple bond, we always know that there is 1 sigma bond and how many pi bonds? 2 pi bonds, okay? Then now 1 sigma, which makes it 2 sigma bonds. This carbon has 2 sigma bonds, so this guy here is sp hybrid, okay? He's sp hybrid. What about this carbon? This carbon is attached to there is 1 sigma bond. Even in triple bond, there is 1 sigma bond, so which also makes it what? sp hybrid. So all in all, since they all have the same, it means the whole entire molecule that has these carbons is going to be what? sp hybridized. sp hybridized. So the whole molecule is sp hybridized. So this is how we check the hybridization of different types of molecules. Okay? This is how we check, because we did mention that hybridization is a process of the mixing of orbitals when they start, the process in which those orbitals are overlapping with each other. The reason why they have to overlap is to create more stable bonds, is to make more stable bonds, when those electrons will be pairing with each other. So that is the main goal of hybridization. It is to create more stability in a way, to create more stability. You get what I'm saying? That's the main goal of the hybridization taking place, if people might be asking themselves a question. Okay, so guys, this was all that I had for you regarding hybridization. If you have any other questions, guys, feel free to comment. Don't forget to like. Don't forget to share with your friends, with the families, with the classmates, and all the people that you feel like they need this help. You know what I'm saying? Send them. Copy the link. Share about TikTok. Share to your WhatsApp. Share wherever you feel to. I love you all. Stay blessed all the time in all that you do. Don't forget to invite God. Nyabonga, I love you guys.